Okay, so we're going to talk about the J73's hydraulically modulated variable inlet guide vane system. This one's far more complicated than the electric modal system. So before I get started, however, there's a couple of things I want to talk about. Namely, well, I wanted to get the model differences out of the way. I didn't talk about that in part one of this series, but so the Dash 3 was the initial production configuration. This included all the firsts, as we discussed in part one of this series, in terms of first use of titanium, first two-stage turbine, and there were some other things. But in addition to that, the Dash 3 was the initial production configuration. The Dash 3A had two primary changes to that configuration. The first is that the PE-3A fuel controller was replaced by the PE-3B fuel controller, and the electrically operated variable inlet guide vane system was replaced with the hydraulic one that we're about to talk about. The Dash 3 model incorporated all the changes of the Dash 3A, and it included an over temperature control of the automatic start system. This over-temp control system was only used for auto starts, and it didn't impact steady state operation of the jet engine. The Dash 3E included all of the changes introduced in the Dash 3D configuration, but it was aimed primarily at weight reduction of the engine. Also to note, all of the Dash 3A, Dash 3D, and Dash 3E all used inertia type fly ball governor micro switches. And these did not include a 76% RPM switch, and the speed switch for these models was not part of the variable inlet guide vane system. So, before I really get into the meat of this, there's a concept that we're going to have to understand to get the most out of this video, and that is corrected engine speed. So, corrected engine speed is the variable that is used by the PE-3B fuel control to schedule variable inlet guide vane position. So corrected engine speed is actual engine speed that's been corrected to account for outside air temperature changes. Kind of to exemplify this, let's say that our compressor is rotating at 50% RPM, and at that RPM it's delivering 50 pounds of air per second as its mass flow rate on standard day condition. And at 40% RPM, it's going to deliver 40 pounds of air per second. And at 60% RPM, it's going to deliver 60 pounds of air per second. So if the compressor is operating at 50% RPM and it's delivering that 50 pounds of air per second, if the temperature decreases, the air density is going to increase to the point where you can have at 50% RPM a compressor that's now delivering 60 pounds of air per second. And on the other hand, if your compressor is rotating at 50% RPM, the temperature increases, your density decreases. So now that your compressor rotating at 50% RPM will deliver only 40 pounds of air per second. So obviously, if we want to get that 60 pounds of air per second, we're going to have to be at 60% RPM. On a standard day condition. However, in that previous example, if we are delivering 60 pounds of air per second and the compressor is rotating at 50% RPM, we can say that the actual engine speed is 50% RPM, but the corrected engine speed is 60% RPM. That's regardless of the actual RPM. So, kind of to sum that up, the corrected engine speed is the speed at which the compressor would have to rotate to deliver the existing mass flow rate on a standard day condition, regardless of actual engine speed. All right, so what we're looking at here is a small diagram of the hydraulically modulated variable inlet guide vane system. I'm going to kind of go over some of the key components in this system before we talk about its operation. So this is the power amplifier portion of your PE3B fuel controller, and this right here is the actuator for the variable inlet guide vanes. And this is kind of an overview of the system. So you have your PE3B controller here. You've got the These lines are going to provide that hydraulic fluid or high pressure. The hydraulic fluid in this case is high pressure fuel to your actuator up here. You've got the bell crank and the two master vanes at the top of the engine. And this right here is that Teleflex cable that provides the feedback to our PE3B controller to so that we can the engine tells this guide vane actuator where to go, and the Teleflex cable is that feedback to say essentially where am I versus what you're asking for. And I've got this. This is a much more detailed diagram of that, and it includes some other stuff off to the side up here, but I don't have a scanner big enough to get the whole sheet because it's an 11 by I think 17 inch scan, and I couldn't get that in here, but I got all the important bits, which is going to be all this down here. Now, the reason I wanted to show this primarily is to show that right here there's a sleeve. That's this little component right here. It's attached to this wheel that's spring-loaded up against this cam. And this piston that cam is attached to is vital in the function of this system. In addition to this sleeve, there's another sleeve right here. Goes on both sides of this piston. We're going to be calling it a cam later, but in this diagram it's called a piston. But this outer sleeve right here is actually connected to your Teleflex cable that's getting that feedback from the actual position of your guide vanes. So just know that you have your inner piston here, and that has a slider on the outside or a sleeve. You've got this cam or piston that also has a sleeve on the outside of it. So both of these have sleeves on the outside. They're going to be kind of hard to see in the next diagram. That's why I wanted to pull this up and show that. Also, this is your actuator, and it shows your two your fluid inlets. So you've got this side that pushes this piston out to extend or the actuator or fully open these vanes, and then you've got this side you port fluid into here to retract this piston and fully close these vanes. So that's what I may pull this up later. I may not. We'll see when we get to it, when we get into the meat and potatoes of this thing. But anyway, yeah, the most important thing is these two sleeves. They are separate components. They move independently of both of the cams. All right, here we are. We're getting into the real meat of this thing. So here's a color-coded diagram. Now this system has three conditions. You've got condition 1, which we're looking at right now, where the engine's rotating at 6,000 RPM. That's corrected engine speed. It's going to be below that. There's a steady state operation where we're talking about between 6,000 and 7,000 RPMs. That's in corrected engine speed still. And then condition 3, which is your RPM is going to be above 7,000. So, all right, so the way this system works, actually before I get there, let me point out this right here is that sleeve that we talked about. And it's going to be, this spring is pushing against this sleeve to keep it as full right as it can. And of course, once the cam or this little bearing contacts this cam is where it stops, but it's going to be spring loaded against that. And then over here, we've got this other sleeve. Again, this one is controlled by this Teleflex cable, which is the feedback from the true position of your inlet guide vanes. And then, of course, this cam right here is going to be controlled by fluid pressure through either port C or port E. So, during operation below 75% RPM, which is that 6,000 corrected engine speed, the corrected speed shaft right here is going to be seated fully left. And so is that speed slider valve, which is this right here. This is your speed slider valve. This allows oil to be ported to the top of the cam, which is item 4, through port C. So you're going to have high pressure oil coming through here, through port D, through port C. The top of this cam is going to push it down. This is also going to allow oil to drain from the bottom of the cam. So we're going to be leaving port E, going back to the hydraulic controller, the PE3B at case pressure. As the cam moves down, so does the high pressure fuel valve. So we're gonna, this cam it's the same component, but they call this in this particular GE manual, they call this the cam and this the high pressure fuel valve, but it's all the components one and the same. So as we port oil through the top of this cam, forcing it down, we're going to open up a pathway for high pressure fuel coming from the high pressure fuel pump through port H, through port L, through port N, and this is going to be pushing this piston to the close the full close position, and we're going to stay in this position until we start getting through to that steady state operation between 75% and 87% RPM, which corresponds to approximately 6,000 to 7,000 RPM in corrected engine speed. All right, so now let's go look at condition 2. All right, so this is going to be our steady state operation. So during operation between these two ranges, our 6,000 to 7,000 corrected engine speed, the IGVs are modulated to some position between full open and full close, and that position is going to be dependent on what the corrected engine speed is. So once the engine reaches that speed of approximately 75% RPM, which again is 6,000 corrected engine speed, speed shaft begins to move to the right. So this is going to start moving this direction. It's going to contact the speed slider valve. It's going to push it to the right. When the speed slider valve is in the position pictured in this diagram, it's blocking port A and port C. So you see that this portion is blocking here, this is blocking here. This cam cannot be moved. It's essentially, it's effectively hydraulically locked in this position such that it can't move. This position coincides with the high pressure fuel valve hydraulically locking the guide vane actuator, port M and port N. So this piston can't move, this can't move because of the speed slider valve and this hydraulic, the high pressure fuel valve that they call it. Now keep in mind, you see also that the our sleeve here has also moved, because as these start to move, remember that this Teleflex cable is causing this sleeve to move up or down depending on their true position. And in the steady state operation, we have a hydraulic lock on our inlet guide vane actuator here and on the cam controlling the position of your high pressure fuel valve. Now, once we move into that high RPM or that let's see here, condition 3, where we're talking about we're above 7,000 RPM in corrected engine speed, we want these inlet guide vanes to be full open. And so what we have here is we've got oil. Oil from port going through port B. It's going to be. I'm sorry, I've got that backwards. We have oil leaving this compartment. High pressure oil is ported to the bottom side of the cam through port E, and that's through this speed slider valve. Its position allows oil to come in through here, pushing this cam up, which opens port K to the high pressure fuel, and that's going to push our variable inlet guide vane to the full open position, allowing high pressure fuel to leave. And you see where the this sleeve in here that's connected to the Teleflex cable opens port L to allow fuel in this compartment to drain back to the low pressure side of your fuel pump. So that in a nutshell is how the system works. Again, there's some other components. There's altitude compensation. I'm not going to get into all of that stuff because that's going to be I don't have the diagram pulled up yet, but there are other things in here that happen, but I didn't want to get too technical. So basically, this is that system. Very ahead of its time. And again, I mentioned, I think in the last video, the J73 and this initial rendition of the modulated variable inlet guide vane system was really ahead of its time. And it wasn't that it was unreliable, it wasn't that it didn't work, and it wasn't that it was too maintenance intensive to be functional. It essentially just a victim of how quick the pace of technology was for gas turbines at this time. Keep in mind that we're talking late 40s, early 50s into the mid 50s. Jet engines weren't really being used in the commercial market yet, which means that they didn't have to be economical, because if the military's paying for them, cost was less a concern than it was in the civilian and commercial world. So as a result of that, a lot of money was dumped into advancing these technologies, and it was a blistering pace. This technology, how quickly it matured and how quickly it changed, and how quickly brand new weapon systems became obsolete because of the quick pace. And again, the J73 was a prime example, and to some degree the J71 also, a victim of this quick pace of technology. And one other thing working against the J73 is the J73 only had one customer, and that was the F-86H. And only 870 of those were built. So as opposed to the J71, used the McDonnell F3H Demon as well as the B-66 destroyer from Douglas, which that had 2 engines per airplane. So a lot more of those were built than the J73. All told, it's a really great engine. Not a lot about it out there, which is why some of this information was so difficult to come across. But that's it. That's the modulating system. I hope someone has enjoyed this. I've certainly enjoyed doing all the research to make this video. And I'm going to be doing more stuff in the future. I plan on doing the fuel system for the J75. If I can find anything for the J58, the SR71 engines, I'll be doing a video about that as well. But in the meantime, I hope you've enjoyed this. It's certainly been fun making it. So thanks for tuning in.